In this video, I wanted to go over this problem dealing with electric potential difference. The first thing we should do is visualize what is happening. There's a proton that's accelerated by an electric field. So I like to visualize the two plates that help me visualize the electric field. If you have a positive plate on one side and a negative plate on the other, you know that the electric field always points away from the positive towards the negative. You know that the electric field also points towards a lower potential. So if you put a proton here, you know that it's going to experience a force to the right in the same direction as the field. So it's going to move to the right, which means if it goes from point A here to point B, that there's going to be a potential difference between those 2 points, because point B here will be at a lower potential than point A. So that's what we're trying to find in this problem. Let's go ahead and write down our givens. We have that the proton is initially at rest, so initial speed or velocity is 0. We have that it moves 5 centimeters, so from A to B, that's going to be our delta x. That's going to be 0.05 meters. Then we have the time is 1 times 10 to the negative 6 seconds. Other things that we know is the charge of the proton. That will be useful as well. The charge of a proton is 1.6 times 10 to the negative 19 coulombs. And we also know the mass of a proton, which is 1.67 times 10 to the negative 27 kilograms. So now let's take a look at our approach. How do we figure out this potential difference? Well, we know that when the proton goes from A to B, that it's going to lose electric potential energy. The potential difference here is actually defined as the change in the potential energy of your proton divided by the charge of that proton. I can call that Q prime. This is the charge that's moving here, the test charge. So in order to find this potential difference, we need to find by how much the electric potential energy changes. So we're kind of working backwards. Well, we also know that if it loses electric potential energy, that means that it's going to gain kinetic energy. That's from conservation of energy. We know that the change in potential energy is equal to the negative change in kinetic energy. So that means that if we can find a change in kinetic energy, we can get the potential energy. So then we need to think some more, well, how much does the kinetic energy change? And that's what we're going to use this information for. We know that the change in kinetic energy is going to be this right-hand side here. Delta K is 1/2 mv final squared minus 1/2 mv initial squared. So this right here is a change in kinetic energy, but it's negative, so we're going to distribute that negative to both terms, and that's going to give us 1/2 mv initial squared minus 1/2 mv final squared. So we can see that with these 3 variables here, if we know the initial speed and the displacement and the time, that we can find V final. Once we know V final, then we'll be able to figure out this change in kinetic energy and relate it to this change in potential energy. So this is just kind of showing you the thought process that we're going to be working backwards here. So the first step that we're going to do is find V final. To do that, we're going to find a kinematic equation that has all of these 4 variables. This kinematic equation has all 4 variables. Delta x equals 1/2 times V initial plus V final times t. So V initial is 0 because it started from rest. Now we need to go ahead and solve for V final. So we're going to multiply by 2, and divide by t, and that's going to give us V final by itself. When we plug in our numbers for delta x and t into V final, we're going to get 1 times 10 to the 5 meters per second. So that's the first step. We can see that our proton speeds up because it's being acted on by the electric field, which is speeding it up to the right. Now the next step is to figure out, okay, what's the change in kinetic energy of our proton here? That's going to be 1/2 mvf squared minus 1/2 mv initial squared. So initially it doesn't have any kinetic energy since it's at rest. So the change in kinetic energy is going to just be the final kinetic energy. We're going to plug in our final speed here and our mass that we have here, and we're going to get 8.35 times 10 to the negative 18 joules. So then step number 3 is going to be that our change in potential energy is going to be the negative of this change in kinetic energy. So I'm just put a negative in front of it. So I broke this down into a couple steps, so I didn't actually use this expression here. I just went ahead and just got the change in kinetic energy and then said, okay, we're going to find a negative of that number to get that potential energy. And now the last step is to look at the potential difference between the 2 points. The potential difference is directly related to the change in energy of that proton. So we're going to divide our change in energy by the charge of the proton, which is right here, 1.6 times 10 to the negative 19 coulombs. We're going to plug these two numbers in, and we're going to get negative 52.2 volts. So let's take a look and visualize this in our picture here. So that's the potential difference between points A and B. So that means that if this point here were at 52.2 volts, then that means that this point here would be at 0 volts because you're dropping 52.2 volts. As far as what the question is asking, it's asking what is this voltage drop through which it moves. So the problem is already telling us that the voltage is dropping, so it's just asking for the amount by which the voltage drops. So the final answer for the actual amount is just going to be the positive number because the problem is already telling us that it's dropping and it doesn't want that negative in there. I hope this was helpful. Let me know if you have any questions.